Hello everybody. So we are in our ninth tutorial class. In this we will be discussing plasma equilibrium and radiation. So we will try to understand the equilibrium, radiation mechanisms and diagnostic techniques. So basic equilibrium concepts and that follows are like this. I just summarize the concept that we have studied in our regular classes. We had CT where all temperatures are equal. Electron temperature, heavy species temperature is same as the radiation temperature. We had LT where local equilibrium was holding and collisions were dominating. We had electron temperature is same as heavy species temperature, but it is not same as the radiation temperature. Then we had PLT, partial local thermodynamic equilibrium. So here only higher excited states were in equilibrium, but not the lower lying ones. So these are CT, LT and PLT concepts that we have studied in our regular class. Then as far as this diagnosis was concerned, this plasma diagnosis, we had this optically thin assumption where photons escape and minimal absorption is considered. So that is an assumption based on which our diagnostics were operating. Then Bremsstrahlung is a continuous radiation due to electron deceleration. Then Boltzmann plot technique we used to determine the temperature from the line intensities. Stark broadening we used to diagnose electron density from line widths. Then Saha equation that gave us the species distribution under ionization equilibrium. So these are the concepts that we have studied in our regular classes, and what we will do, we will try to apply them in this tutorial. So the basic radiation laws that we have studied in our regular plasma classes, that one is Planck's law that gives the spectral energy density distribution of a black body, that is U nu T is equal to 8 pi h nu cube by c cube 1 by exponential h nu by kt minus 1. Then we had Stefan Boltzmann law that gives the total emitted power of a black body as P is equal to sigma T4. We had level population according to Boltzmann distribution that gave you Nj by Ni equal to Gj by Ji exponential minus Ei by Kt. Then we had from this, it followed that Boltzmann plot equation which gives you like this, that gives you the temperature from the line intensity. So where I is the intensity, lambda is the wavelength that has been emitted, and Ej is the upper level of the energy, G is the degeneracy, and A is the this transition probability. Then we had this Saha ionization equation in explicit form. It goes like this. This is a generic type where Ni plus 1 is the I plus 1 ionized state, Ni is the ith ionized state, N is the electron density, and this Z is the partition function, and Xi is the here whatever is the exponent, Xi is the ionization energy. So these are basically the radiation laws in plasma that we should keep in mind. When it is black body, it should emit like this. Then level population should occur like this, Boltzmann distribution. Then if we, as a corollary of that, we get this Boltzmann plot equation which allows us to determine the temperature from line intensities using a linear plot. Then this Saha ionization equation gives us the equilibrium population, and then the total emitted power from a black body can be estimated using Stefan Boltzmann law. So this one. So this is the way we can visualize the radiation behavior from a plasma. Now we come directly to the numericals so that we can make our understanding more concrete. So first one, we go for the application of the Boltzmann distribution. So here we are now taking a problem where the population ratio N2 by N1 between two energy levels in a plasma is measured to be 0.05, okay, N2 by N1. And if the energy difference between the levels is 3 electron volt, calculate the plasma temperature, okay. So somehow you are able to know the level population ratio, and you know the gap between the levels, and therefore you are asking to find the temperature of the plasma. So we should apply the Boltzmann distribution. So N2 by N1 is equal to G2 by G1 exponential minus delta E by KT. Delta is the energy gap between the levels. Now here this G values G2 by G1 is given to be 2. So we take that ratio. Then N2 by N1 there it is given that it is 0.05 and delta is 0.3. So G2 by G1 is given. So these are the parameters that has been given. So how do we find the temperature? So if you take this formula directly you can reach here that T is equal to, take this T, delta E divided by Kb log of G2 by G1 by N2 by N1. Okay. So the temperature can be directly obtained from this once you know the G2 by G1, N2 by N1 and delta E. So just I have extracted the T from this relation, it comes to be like this, and what you are getting? T, you just put all the values. So delta is 3.0, then Kb, you know that in electron volt it comes like this, then logarithm is here, this argument is G2 by G1 is 2, N2 by N1 is 0.05, that has been given. You just get this value evaluated over here. So 3 by 8.617 into 10 to the minus 5 and this log of 40. So finally you get a temperature around 13,500 Kelvin, which is very reasonable one for a thermal plasma. Okay. So you just see that from this simple relationship you are able to estimate temperature of the plasma. But you know that for experimentalists they have to look into many other things. Just from a single data it may not be correct to conclude on the temperature. You can get some temperature, but how correct that is, because there are experimental uncertainties and instantaneous deviation in the system itself. So if you want to actually conclude, then you need to take many more precautions that will be coming later, and you are just having an idea, okay, the equation can be applied to find out the temperature. So that idea you are getting from here. So that is the purpose of this tutorial. Now I go to the next numerical one, that for a hydrogen atom at 10,000 degree Kelvin, Kelvin is missing over here, you should write that. Calculate the ratio of ionized to neutral hydrogen atoms if the electron density is 10 to the power 16 per centimeter cube. That is given there unit. Now how will you do that thing? We will go for the Saha ionization equation, and there it says that under equilibrium any NH plus, so the which one is ionized, so ratio of ionized neutral to neutral hydrogen, that it requires. So Saha ionization equation already gives that. So NH plus divided by NH, H is not ionized one. So that is equal to, what is that? So 2 pi m kT by H square, T is given 10,000 Kelvin, and rest of the things you already know, everything is constant, all the parameters are some constant or other. Then exponential E ionization. So ionization energy of this hydrogen atom, everybody knows it is 13.6 electron volt. Now Kb is Boltzmann constant, T is the temperature, that has already been given. So we can find out the NH plus by NH, that is the fraction that got ionized. Actually it should be NH plus by NH plus NH plus, but the fraction is so low, so NH, and if you even add that, that remains more or less the same, and we get the same fraction. So here we put the N equal to 10 to the power 16 as given electron density, E ionization we know 13.6, then temperature is 10,000 Kelvin, and mass of electron we know. So we just estimate this factor 2 pi m kT by H square, it is coming to be 2.4 into 10 to the power 15 per centimeter cube. Then exponential part E ionization 13.6 divided by kBT, we have put in electron volt because this is also in electron volt. Now now K into T, this gives in electron volt, so this should be dimensionless, so this is done, and this exponent is 1.4 into 10 to the power minus 7. So we now put that all these things over here to get the NH plus by NH, and what we find that it is coming to be this 2.4 10 to the power 15, this one given, then NE we have put over here, that already given, that 10 to the 16, and what we get the value, that 0.034. So that is around only 3.4% of the atomic hydrogen is ionized at 10,000 degree Kelvin. Okay, so this formula is giving you that the ionization fraction is quite low, even at 10,000 degree Kelvin, and even for this hydrogen, okay, where only one proton is trying to pull the electron. Then also at 10,000 degree Kelvin you are getting only 3.4% of atomic hydrogen ionized. So you just keep this idea that if I am raising the temperature, it doesn't mean that all of them will get ionized. So 10,000 degrees is a quite high temperature for us, because we know that tungsten is having a melting point of 3,500 Kelvin or so. Okay, so compared to that, this is a quite high temperature, but it doesn't mean that even the hydrogen atom, all of them got ionized. So it is only partially ionized, and what fraction? It is only 3.4%. So that is something to remember. Now this is the 26th numerical in this tutorial series. So this problem says that the Stark Borden line width of a hydrogen Balmer line is given. It's to be 0.5 nanometer. So from that burning, we want to find out the electron density. We have already read in our regular classes that how to find the number density from the Stark Borden line. We have seen those diagrams and all, where the burdening happens, how it looks a line when it is burdened, and usually H alpha and H beta lines are very common to use for this number density calculation. Now in case of this H beta line, the constants appear like this: the delta lambda Stark Borden, this width halfway that full maxima, that is equal to 2 into 10 to the power minus 11. This numerical value is particular to this H beta line, Ne to the power 2 by 3. So once you know delta lambda, that is 0.5 nanometer given over here, then you can easily find out Ne just inverting this relation. So delta lambda Stark by 2 into 10 to the power minus 11, and this 2 by 3 goes as 3 by 2 because we have inverted it. So the number density comes here to be 3.95 into 10 to the power 21 per meter cube. So this is a typical number density that you achieve in your thermal plasma regime, and in non-thermal plasma usually you get a bit lower, say 10 to the power 17, 18 kind of per meter cube number density you get. So this shows that this is a thermal plasma, and what you got over there, that the ionization is kind of 3.4% is also very typical to thermal plasma ionization, because there you get a temperature only around 1 eV, so which is 11,600 degree Kelvin. So there you get a ionization which is not very high, it is like that only 3.4% or so. So this is the last tutorial we will be having in this. No, there is another one. So this one actually the last to last actually that problem. So what it is shown here, a plasma emits a black body radiation at 6,000 degree Kelvin, and calculate what power radiated per unit area. So sigma T4 law will be using, and we know the sigma, and I always try to inform you that this constant is having a very beautiful relationship, that all the digits starting from 5, 6, 7 and 8 appears here. This is a very interesting constant, where all these numbers, this 5, 6, 7 and 8 appears in a serial manner. So it is very easy to remember, that's why I never forget it. So this sigma is there, and then the power radiated is sigma T4. So you just use that, and what you are seeing that this is 7.35 into 10 to the power 7 watt per meter square. You know that such kind of plasma you can find in the corona region of the sun. There the temperature is quite low compared to the core, and the kind of power that is getting radiated per unit area, it may be a bit more than that, but nearly similar. Now what I go actually, so this is just to give an idea that if this is the radiating as a black body, then if this is the temperature, just this is the temperature, the kind of power radiated is see 10 megawatt per meter square. So it is megawatt per meter square of the order. So this is quite high if it is radiating as a black body. Now coming to the last tutorial in this session. So as I told you that experimentalists have a they do have a different trick to find out the correct value, with utmost accuracy they can manage. So they try to find out. So in the first tutorial you have seen that you are trying to find out the temperature directly from the Boltzmann relationship, but here what we are doing, that we are getting the intensity. That is exactly what you measured using a spectrometer. You can find out the intensity. Now, Boltzmann plot technique says that if you plot this parameter, say y, as a function of Ej, the energy of the upper level where from the emission is taking place, then you get a relationship y equal to mx plus c kind of thing, where m is 1 by kt. And when you know the slope, then you know 1 by kt, and then you can find out the temperature. So that is the principle. Now the data that has been given, that there are two levels, one is energy as 2.0, another is level 2 3.0 electron volt. Statistical weight of these two levels are given. Intensity in arbitrary units is always in arbitrary units, because the fiber that you are using, it may have different kind of absorption. So you cannot just specify what absolute unit for this intensity that you are getting. But anyway, whatever intensity you are getting, if you are using the same setup, so the loss factor is always the same to all the fibers, and you can always rely on the values, although it may be in arbitrary units. So wavelength, what is there? So this is 400 nanometer, 500 nanometer near the green region, and the transition probabilities you are getting is this thing. So these are two levels, parameters you have got. Line intensity for corresponding to this level you are getting as this 50, and this levels you are getting 20. And the statistical weight factor, wavelength, transition probability for these levels are given. So what I will do actually, now I will come to here. This involves what? The wavelength, you know the statistical weight factor, you need to know the transition probability. So all of them given, lambda also given. So this y, this log of this one is known. Now you have two values, one is y1 for level 1 and y2 for level 2. Similarly, correspondingly you have E1 for level 1 and E2 for level 2. So basically you know that this is a straight line formula, and you have got 2 points of that straight line. So you know the 2 points x1, y1 and x2, y2 of a straight line, then you know how to find out the slope. The slope is y2 minus 1 y1 by E2 minus E1. So here E is acting as x. So you just put these values, what you y1 and y2 got. Y1 in the first case is 9.21 negative sign, then y2 is minus 11.21. So you put these two values over here, and you are getting a slope of minus 2.08. It is a negative slope. You see that negative sign over here. Okay. So it is 2.08 minus, so that is the slope, and that is equal to minus 1 by kt. So you just invert this relation, and you get the value of T as 1 by 2.08. But here everything is in electron volt we have used. So the temperature is coming to be 0.48 electron volt. So if we convert that into the actual Kelvin, 11,600 is 1 eV. It is just half of that. So it is around say 5,500 or so Kelvin. Okay. So now from this just Boltzmann, how to use the Boltzmann plot technique when you are getting just the intensities, and those intensities are in the arbitrary unit, So then also you can find out the correct temperature using this kind of formula. Okay. Uh, so you are getting a temperature of 0.48 electron volt in this problem. So that is how you can use the Boltzmann plot technique into real problem, but in real problem the experimentalists do not stop at 2 points, because if one point is in error you will get a wrong result, because using 2 points you can always draw a straight line, because there are only 2 points, you can connect them and you will get a straight line. But if you are taking say 10 number of points and you are trying to fit a straight line, then even if there are error involved in 1 or 2 points, you will be getting an average slope which is quite reliable. So experimentalists always go for multiple emission levels. So maybe easily it can be say more than 10. So when you are using so many number of lines, the error involved in the measurement get reduced quite a lot. But essentially the principle remains the same. So this is the principle which you use to determine the temperature. So this numerical, I hope that it clarifies the idea about how to use the Boltzmann plot technique to find the temperature in a real problem. So I hope that you have enjoyed this tutorial, and meet you in the next tutorial in the next week. Thank you.